Hello again, and welcome back to another episode of the CCQTA Lunch and Learn series. I'm Dave Murray, Secretary to the CCQTA and Principal Consultant at Omnicon Consultants. This is our first episode on crude solubility, stability, and blending. The first goal of this series is to provide an understanding of the compositional differences between crude oils and how those can impact blending operations at both midstream terminals and refinery operations. Secondly, it's to provide a basic understanding of the analytical tools that are available to estimate or predict blend compatibility when considering blending two or more streams together. In this episode, we're going to focus on two areas. The basics, which is a basic background on hydrocarbon structures and how those are incorporated into the makeup of crude oils, and how those structures impact the solubility and stability of a crude oil and subsequent blends. The basics. Firstly, we'll do a quick review of hydrocarbons, their atomic configurations, and the diagrams used to easily depict those configurations or structures, kind of like a hydrocarbon shorthand. This will help make sense of the more complex structures we're going to look at a bit later. Then, we'll look at those structures and how they apply to the composition of crude oils. Let's start with the basics. A hydrocarbon molecule is made up of, well, you likely guessed it, carbon and hydrogen atoms. The number and arrangement of the carbon atoms determine the behavior of the associated molecules. These molecules can be represented by ball and stick diagrams. For example, here's methane with 1 carbon and 4 hydrogens, then ethane with 2 carbons and 6 hydrogens. Next you have propane with 3 carbons and 8 hydrogens. Now you get the basic idea that it's like building a chain. Also notice that beside the name of each molecule, I have a smaller diagram also representing that molecule. These are effectively the same as the ball and stick diagrams, but the hydrogens are simply implied instead of included. As you can imagine, as more and more carbons are added, these diagrams get very complex. As the number of carbons increase, so are the options for where they can go in the overall structure. These are called isomers. Each isomer has slightly different properties from the others. These properties include boiling point, density, solubility, etc. As you can see, propane really has no configuration options besides a straight chain. However, as more carbons are added, we see more configurations available. For example, butane C4 has 2 isomers, pentane C5 has 3 isomers, and hexane C6 has 5 isomers. You get the general idea that more carbons means more isomers. Let's look at a few more configurations that are relevant to our discussion here. First, let's start with another isomer of hexane. It has 6 carbons, but they're arranged in a ring structure and is referred to as a cyclic molecule. This one is called cyclohexane. The next configuration also has 6 carbons, but in this case 6 of the hydrogens have been replaced by double bonds. This represents benzene, which is a primary unit of aromatics. The double bonds give aromatic molecules polarity, which changes their solubility properties. Note the addition to the line diagram to indicate the double bonds. Lastly, we have a double aromatic structure, which is the base structure for polyaromatic hydrocarbons, or PAHs. These grow with the addition of more aromatic rings. These structural descriptions and their associated diagrams are intended to provide a basic understanding of the much more complex structures we're going to look at moving forward. The number of isomers for each additional carbon number increases rapidly to the point where there are so many isomers that it's impractical to consider the properties of each. This chart illustrates the number of isomers for each carbon number. I've only gone out as far as carbon 13 and already there are 802 possible isomers. By C30, there are over 4 billion possible isomers, and that is only considering single bonded carbons or saturates. Now let's consider a crude oil which has hydrocarbons ranging from C1 all the way out to C100 and beyond, and imagine how many isomers might make up the whole composition. The complexity of crude oil lends itself to an evaluation of the bulk properties as opposed to the individual components of the composition. Crude oil can be broken down into the following compositional classes that represent the various structural classes and their associated behaviors. In particular, we are interested in the solubility behavior of these classes. There are 4 common classes: saturates, also referred to as alkanes, aromatics, resins, and asphaltenes. These make up what is commonly referred to as the SARA. These are examples of some of the complex structures that can make up each class. Saturates are made up of carbons with single bonds. These can include straight chains, branch chains, and cyclics. Aromatics include one or more benzene rings and can include saturate chains and or cyclics within the structure. Resins have multiple aromatic rings, also called polyaromatic hydrocarbons, which gives them polarity. They can also include saturates and heteroatoms such as oxygen, nitrogen, sulfur, etc. within that structure. Asphaltenes also contain polyaromatics and also contain heteroatoms such as nitrogen, sulfur, nickel, and vanadium. These tend to be very large structures with high molecular weights in the range of 800 to 1,000 grams per mole. These are commonly identified foulants in many applications. Let's have a look at some examples of different asphaltene structures. There are two main types of asphaltenes. Continental type, illustrated in the top right, which are comprised of a large polyaromatic core with branches on the outer edges, and archipelago type, seen in the bottom right, which have smaller polyaromatic islands connected by saturate chains. Different regions also have different asphaltene types. For example, in the top left is an example of asphaltenes from Venezuela, which have a continental structure, while the bottom left is asphaltenes from Athabasca, which have a more archipelago structure. Both types of asphaltene structures may be present, however one is generally more dominant than the other in a particular region. Keep in mind that these are postulated structures based on many years of research, but the actual structures in different configurations are countless. This is just an example of a pipe section fouled with asphaltenes. The loss of inner diameter is pretty obvious and would limit the volumetric flow capacity of that section of pipe. Now let's have a look at how the actual SARA classification is performed in the lab. I want to discuss this method because there are a number of different methods and variations in use, including, but not limited to, ASTM D2007. One of the most significant causes of error in SARA results actually occurs during the initial preparation. The first step of almost all test variations is to initially cut the sample at some temperature to avoid loss throughout the remainder of the test. A vacuum distillation is performed to split the sample, for example, into less than 200 C and greater than 200 C fractions. The less than 200 C fraction ideally is then analyzed by gas chromatography to quantitate the amount of saturates and aromatics in that fraction so that they can be included in the mass balance later. However, another common practice is to simply use a predetermined ratio of the saturates to aromatics and apply that to that mass fraction. For light samples which may have a large light fraction, this can impact the final SARA ratios. Coming up, you'll see why correct SARA data is important. Now, the greater than C fraction moves into deasphalting. This is done by contacting with an excess of pentane. The pentane soluble fraction is then vacuum distilled to remove the pentane, leaving behind what is referred to as the maltenes. The maltenes are then loaded onto an alumina-filled column for further extraction by column chromatography. Successive solvent extractions based on polarity and solubility are then used to separate the remaining fractions. First, with heptane to extract nonpolar saturates, then with toluene to extract aromatics, and finally, a highly polar mixture of dichloromethane and methanol is used to extract the resins. All of these fractions, including any mass loss, are then combined to calculate the SARA results of the crude. Note the use of polarity to separate the individual fractions. Asphaltenes are very polar, making them insoluble in nonpolar saturates. Resins are also polar but have nonpolar characteristics within their structure, so they are stable in nonpolar solvents. That way the asphaltenes can be removed without impacting the resin fraction. Aromatic rings are unique and have a high affinity for each other, so toluene is used to extract them. And lastly, saturates are nonpolar, so they are soluble in nonpolar solvents such as heptane. Remember that like dissolves like and the opposite. As a final note on this method, when providing results in test reports or assays, I would encourage users to identify the initial distillation conditions as well as the method used in determining the saturates and aromatics of the light fractions. That way users of the data understand the conditions and if other SARA results can be compared directly. Now that we have a basic understanding of hydrocarbon structures, let's delve a little deeper into solubility and stability as it applies to crude oil. When we're talking about crude stability, we're primarily talking about asphaltene stability. Given asphaltene's wide structural possibilities, they are a class of molecule identified primarily by their lack of solubility in low molecular weight saturates, typically C5 or C7. When a sample of crude oil is contacted by an excess of pentane or heptane, asphaltenes are destabilized, agglomerated, and then precipitated, which allows them to be quantified by filtration. The following microscope images show the quantity and agglomeration properties of asphaltenes when a heavy oil is contacted with C7. This is a crude prior to heptane addition. This is the same crude with a 4:1 heptane addition. And lastly, after a 9:1 heptane addition, you can clearly see the impact heptane has on the solubility and stability of asphaltenes in crude oil. Keep in mind, this is also at a microscopic scale, so evidence of precipitated asphaltenes in operations may take time to appear as fouling. Previously, I spoke about the ability of pentane and heptane to precipitate asphaltenes. These images also illustrate the difference in type of asphaltenes that are precipitated based on the type of solvent used. The left-hand images shows asphaltenes that are precipitated using C5 and the right-hand image with C7. The C5 asphaltenes are more brownish in color and have a crumbly texture, while the C7 asphaltenes are black and shiny and have a more brittle texture. Since crude oils typically contain a continuum of carbon numbers, both C5 and C7 are likely present, so both types of asphaltenes may be precipitated when blending crudes together. While saturates have a tendency to destabilize asphaltenes, aromatics and resins both have a stabilizing effect and prevent precipitation. This is due to the aromatic ring structures contained in all three. Therefore, the higher the aromatic and resin content, the more stable the asphaltenes. Saturates have the opposite effect and destabilize asphaltenes and result in precipitation. Since we know that saturates destabilize asphaltenes and aromatics and resins stabilize asphaltenes, the overall stability can be predicted mathematically. The mass ratios determined using the SARA test method can be used to determine the ability of a crude to keep asphaltenes stable and in solution or dispersed. The colloidal instability index, or CII, is used to predict the stability of a crude oil or a blend of crude oils. It is simply the ratio of the sum of saturates and asphaltenes divided by the sum of aromatics and resins. After collection of many years of data, researchers have identified a CII stability criteria. Crude oils with a CII of less than 1 should be stable, meaning they have sufficient solvating power to maintain asphaltenes in solution. Crude oils with a CII of greater than 1 are likely unstable, meaning they have insufficient solvating power to maintain asphaltenes in solution. Another common term for this type is self-incompatible. These are examples of 6 crudes ranging from light to heavy with their SARA composition. The 2 light crudes are a good example of the impact of aromatics and resins on stabilization. Light crude 1 has 10 times the amount of asphaltenes as crude 2, but also has more resins and aromatics and less saturates than crude 2. Light crude 1 has a CII of 1.8, while light crude 2 has a CII of 7.5. While both are above the CII limit of 1, if you're looking to blend these with other crudes, you may consider number 1 instead of number 2. On a mass basis, these are additive. So from a blending perspective, you can use the sum of the mass fraction of each crude to determine the contribution of each of the SARA components to determine the CII of a theoretical blend. Let's take a look at an example of blending various crudes and the resulting CII of the blended product. Imagine you have 3 crudes entering your facility and you'd like to understand if they may become unstable and cause problems. Assuming you have reliable SARA data available for all 3, you can calculate the CII of each crude and use those blends to predict the stability of possible blends. Scenario 1 is a simple 50-50 blend of crudes 1 and 2 and has a CII of 1.3. Scenario 2 is a blend of 20% crude 1 and 80% crude 2 and has a CII of 1.0. Scenario 3 is a blend of 70% crude 1 and 30% crude 2 and has a CII of 1.5. And lastly, Scenario 4 is a blend of 10% crude 1, 70% crude 2, and 20% of an opportunity crude that's been suggested. This blend has a CII of 1.7. Now, if you remember back to the CII criteria for stability, it indicated anything below 1 should be stable and anything above 1 should be unstable. That means of all 4 blends, Only blend 2 indicates stability. Now, CII is only one of the tools that is available to predict stability, so keep in mind that predictions are theoretical and not always true in real-world situations where other variables can also influence stability. Therefore, calculated empirical stability may not match. Now let's move on to physical solubility testing. As we've discussed, when we are referring to crude oil stability, we're really talking about asphaltene stability in the crude. As you might expect, physical solubility testing focuses on asphaltene's ability to be precipitated and or dissolved. ASTM 8253 was developed by CCQTA and published by ASTM in 2020. This is a relatively simple microscopy method used for identifying asphaltene solubility in a crude oil. However, the solubility parameters determined using this method are quite powerful when used for calculating blend compatibilities. We'll get into that in a little more detail later. The D8253 test method is separated into 3 embedded procedures. Procedure A for samples with asphaltenes, Procedure B for samples without asphaltenes that have low solvency, meaning they act like heptane, and finally Procedure C for samples without asphaltenes that have high solvency, meaning they act like toluene. The last 2 are unique to this test method and allow evaluation of all types of crudes. Now, the initial steps of the method does do a preliminary screening to establish which procedure to use. Now, let me summarize the 3 procedures so the differences are clear. Procedure A for samples with asphaltenes. The sample is contacted with heptane to precipitate asphaltenes. Then toluene is incrementally added and observed under the microscope until asphaltenes are no longer visible. The above is repeated with 2 additional sample masses. Then the data is plotted and the solubility parameters are calculated, including the FR max, P0, and P value. Now I'll give you an example of the calculations shortly. In Procedure B, for samples without asphaltenes having low solvency, so acting like heptane, a known reference oil with asphaltenes is contacted with sample instead of heptane to precipitate asphaltenes. Then toluene is incrementally added to the mixture and observed under the microscope until asphaltenes are no longer visible. As before, the above is repeated with 2 additional sample masses, and the data is plotted, and only the P0 is calculated because there was no asphaltene, so you cannot have an FR max. In Procedure C, for samples without asphaltenes but with high solvency, meaning they behave like toluene, a known reference oil with asphaltenes is contacted with heptane to precipitate asphaltenes. Then sample is incrementally added to the mixture and observed under the microscope until asphaltenes are no longer visible. The above is repeated with 2 additional sample masses, same as the other 2 procedures, and the data is plotted and the P0 is calculated. Next, we'll look at an example of the microscope observations, calculations, and interpretations. These are the microscope images of a sample that is asphaltenes run using Procedure A. At the starting point with 9 mL of heptane and 1 mL of toluene, there's a significant population of asphaltenes observed. As more toluene is added, such as 3 mL, 4.5 mL, 5 mL, you can see the population decreasing. There's 5.4 mL, 5.6 mL. Also note the smaller volume increments of the toluene additions as the asphaltene population nears 0. There's 5.8 mL and finally 6 mL. There is only a slight difference between 5.8 and 6 mL, so the endpoint is estimated at 5.9 mL. At the endpoint, it provides our first data point in the series of 3. This test is repeated with increasing masses of samples, starting with 1 gram, then 2 grams, and finally with 3 grams, although smaller or larger masses are permissible to ensure the endpoint is reasonable. This is the data from the microscope observations we just looked at. There are 2 values that are calculated. First, the dilution number, which is effectively the volume percent of sample at the endpoint, which in this case is 7.2. Next is the flocculation ratio, which is effectively the volume percent of toluene at the endpoint, which in this case is 39.6. The dilution ratio and flocculation ratio are plotted for each sample mass, and then the solubility parameters are calculated. The maximum flocculation ratio, or the FR max, equals the y-intercept. The critical dilution number, or D crit, equals the x-intercept. The remaining parameters are calculated based on these first two. The P0 is the FR max times 1 plus 100 over the D crit, and in this example the P0 is 114. Now I'll give some further context to this value in a moment. The P value is the P0 divided by the FR max. This can also be referred to as the peptizing power. Procedures B and C will be described in more detail in the next episode, which will serve as a tutorial for the 8253 test method. Now that you have the D8253 solubility parameters, what can you do with them? Firstly, since all products have a P0 value, but only those with asphaltenes have a P value, we can use the P0 to compare the asphaltene solubility of one product against another. When looking at this chart, the P0 value gives you an idea of the asphaltene solubility compared to toluene, which has 100% asphaltene solubility, and heptane, which has 0% asphaltene solubility. I've also added pentane and butane to illustrate where they would fall on this chart. They're important to consider when considering products for blending. If products are high in pentanes and butanes, etc., then the P0 values will also be very low. Here's some examples of heavy, medium, and light crude P0 values. H1 is a heavy crude with a P0 greater than 90, indicating it has good asphaltene solubility and is not only stable but has good solvency for asphaltenes, so it is favorable in a blending scenario. By comparison, L1, which is a light crude, has a P0 around 10, indicating it has a very poor asphaltene solubility, so it is not favorable in a blending scenario with something that actually has asphaltenes. This next chart shows the inverse relationship between the logarithms of both CII and P0 for a series of crudes ranging from heavy to light. As the CII increases, the P0 decreases linearly. This also shows the excellent correlation between the composition from which the CII is derived and the physical solubility from which the P0 is derived. Given that the SARA methodologies used in industry can vary significantly, the D8253 is more reliable to determine stability and solubility. What the 8253 method also provides is a visual confirmation of the presence or absence of asphaltenes. Based on the solubility testing and the development of the calculations of the solubility parameters, stability guidelines have been established for crudes with asphaltenes. Crudes or crude blends with p-values of greater than 1.2 are generally considered stable, while p-values of 1.2 or less are considered unstable. Handling or processing unstable crudes runs the risk of desalter upset, emulsion formation, heat exchanger fouling, tank bottom buildup, deposition in pipelines, etc. Crude blending is the most useful application of the solubility parameters from D8253. The solubility parameters from two or more crudes can be combined to identify stability limitations for a given blend recipe, which can be critical in preventing asphaltene-related process issues and fouling. Let's look at how the solubility parameters are applied in blending. Blending calculations have a few conditions that must be met. First, the solubility parameters for each crude must have been determined using the same method such as D8253. Next, one or more of the products must have a P0 and an FR max value. Next, products with only a P0 value will have an FR max of 0. And lastly, the product with the highest FR max will be the FR max of the overall blend. The blend calculations are as follows. The P0 of the blend is the sum of the volume fraction of crude A times the P0 of A plus the volume fraction of crude B times the P0 of B, and so on and so forth, all divided by the sum of the volume fractions of each crude. From there, the p-value of the blend can be determined. Remember, the FR max in this case is the highest FR max of the blended crudes. Using the highest FR max makes for a conservative prediction, meaning the predictions err on the side of caution. Now let's look at a few examples to illustrate these calculations. This first example is of blending a heavy crude with a P0 of 110, an FR max of 44, with a light crude with a P0 of 10. The scales on the left indicate the volume percent of each crude in the overall blend. The P0 of the blend is calculated based on the volume ratio at each line. The FR max 1 is the maximum of the individual crudes. Those values are used to establish the P value at each volume ratio. And note the right-hand column indicating the stability. The upper section shows the blend ratios that are not compatible. The middle section shows blend ratios that are theoretically stable, but if conditions change such as temperature, they may become incompatible. And temperature may negatively or positively impact the stability of the blend, but better aim for higher stability either way. The lower section shows blend ratios that should be stable under most circumstances. The last thing to note about this data is the blending order. Starting blending with 100% of the heavy crude and then blending in light crude yields stable blends, in this case up to 50-50. However, that is not the case starting 100% light crude and blending in heavy crude. In the heavy to light scenario, top down, immediately the blend is incompatible, so asphaltene precipitation will be at maximum. This is a similar example, but a third crude without asphaltenes has been added to the blend. In this case, the addition of a medium crude with a higher P0 than the light crude increases the zone of blend stability. Again, as long as the blend order of light into heavy is strictly adhered to. This last 3 crude blend uses a heavy crude with a high P0 and adds a medium crude that also contains asphaltenes and has an intermediate P0. This blend has a stability region even higher than the last example, again as long as it's blended in the correct order of light into heavy, so bottom to top. Note that the medium crude does have an FR max, however the FR max of the heavy crude is still higher, so it's used in the p-value calculation. Let's summarize what we've talked about today. First, we talked about basic hydrocarbons and the diagrams used to depict the various structures. That led to the discussion on classification by compositional properties as opposed to individual components. From there, we discussed the 4 classes being saturates, aromatics, resins, and asphaltenes, otherwise referred to as the SARA. Then we briefly discussed the SARA test method and some common pitfalls. Next, we discussed the SARA ratios in terms of solubility and stability, and the calculation of the colloidal instability index, or CII. From there, we moved on to using the SARA and the CII to predict blend stability and compatibility. Then we moved on to talk about physical solubility testing using the publicly available ASTM D8253 test method and describe the embedded procedures within. A strong correlation was shown between the CII and P0 value. Lastly, we discussed using 8253 solubility parameters to predict blend stability at various ratios of different crudes and how blend order is critical to ensure stability when blending. Thanks for watching, and I look forward to connecting again. If you'd like further information about this topic or any other topics the CCQTA is working on, please visit our website at ccqta.com. If you have any feedback, please send it to secretary@ccqta.com. Please check back regularly for new additions to our Lunch and Learn series and other videos.